So we're going to talk about free body diagrams and their role in solving Newton's law problems. Um, and I'm just going to work through a couple of examples. The key to solving Newton's law problems is using Newton's second law. It's being able to plug in into these two equations. Usually you're looking for a force or an acceleration in the x or y direction, or maybe both. And so the key to solving the problems is being able to set up your forces in such a way that they're easy to plug into these equations. And really most of the hard work in solving Newton's law problems is getting these diagrams right so that you can get all your forces plugged in into the correct coordinate system, into the correct component, so that your solutions come out right. Um, so most of the time, all of these forces that we're using are acting on a particular object. And so every time we work a problem, we'll be saying, well, what's the object of interest here? Often it's obvious. In our examples, it'll be obvious. But in more complicated examples, which we'll do later on, it's not as obvious. And so I'm just going to work through a couple of examples. We're going to identify what the relevant object is. We're going to identify the forces acting on the object, and we're going to show the role of the free body diagram in solving the problem. So this is an example of how we use a free body diagram to solve Newton's law problem. Let me get a color here. So we have a block of mass 2 kilograms. Let's just call it M, right? It's being pushed horizontally across the table by a force F is 10 newtons. There's a friction force of 5 newtons. This hasn't been labeled, so we'll just call it F sub F for our purposes. And it says, what is the acceleration of the block? And so it's asking us something about the block, and so that tells us our object of interest is the block. It would be hard to get that wrong in this problem, but there are problems where there are multiple objects. And so we're just going to draw a little picture. Here's the block, right? And here's the horizontal surface. And so we just start drawing our forces. Here's the force F, that's 10 newtons. Here's the force of gravity that's acting downward. We're going to have a normal force that's acting upward. We'll call it F sub n. And then back here somewhere, we have a force of friction, right, which is 5 newtons. And we've addressed all of these things, right? We can write them off to the side here. We can say F is 10 newtons, 10 newtons, F sub F is 5 newtons, right? F sub G is 20 newtons, right? And we could determine pretty quickly and directly the normal force, but we'll get to that if we need it. And so our goal is to solve for the acceleration. So we know it's going to come from our Newton's law equations, and those are sum of the forces in the x direction, make that look like an x, is equal to ma sub x, and the sum of the forces in the y direction equals ma sub y. Now, when we draw these diagrams, if there are multiple objects, there can be forces acting on different things. Here, all of the forces are acting on our object of interest, and that's good. We haven't drawn forces acting on the ground due to the block, for example. And so, so our next step, which is to draw a free body diagram, let me get a different color for that, right? And I'll just put a free body diagram up here. And the purpose of the free body diagram is to get this problem ready to plug into these equations and solve. And so when we're doing a free body diagram, we take our object of interest and we just represent it as a dot. So now our block is a dot, and we draw all the forces on it. Here's the normal force. Here's the push force. Over here is the friction force, and here's the weight. Now we could say we can just kind of plug into these guys, except we really haven't identified a coordinate system, so we don't know which is the x direction and which is the y direction. And for more difficult problems, this can be really complicated. And so the way we identify our coordinate system is we identify first the direction of the acceleration. In this problem, we don't really know if there's an acceleration, but if there is one, it'll probably be along the horizontal direction. So if you don't know what it is, you can just put a little question mark there and make an estimate of where you think the block is accelerating. And that allows us, knowing the direction of our acceleration, allows us to pick a coordinate system. The key to picking a coordinate system is to put one of its axes, you know, the plus x, the minus y, or the minus y, right along the acceleration. And so in this problem, I would just use a standard coordinate system where this is my x, the horizontal is my x, and the vertical is my y. That allows me to say, oh, my x direction forces in Newton's second law are the force of friction and the push force, and my y direction forces are the normal force and the force of gravity. And this is what allows me to then start plugging in and determining the acceleration of this object. So the purpose of the free body diagram is to get everything ready to plug into these equations. And once you've got that free body diagram done, you've really reduced your problem to just a bunch of math that you will have done a lot of times by the time you get to it. So on the next page, we'll start from here and we'll go ahead and solve that problem. So here's our free body diagram that we drew right at the end of the last screen. And let me just go ahead and write down some of the, I'll use a yellow here, right? We said that the mass of the object, we said that the mass of the object is 2 kilograms. The friction force is 5 newtons. The force which we have written there is 10 newtons. We knew that the force of gravity, right, is 20 newtons. And so we can then come over to these equations and say, look, the sum of the forces in the x direction equals ma sub x. Once again, I encourage you to always start with this equation. We're interested in the acceleration. As it happens, all of our acceleration is in the x direction. This is why in the last, when we selected our free body diagram, we put one of the axes along the acceleration. That way one of our sums gives ma and the other one gives 0. It simplifies our math. We don't have components for our acceleration. And so the sum of the forces in the x direction equals ma sub x. We can just call that ma because all of our acceleration is along the x direction if it's accelerating. And so now this part of the equation, the sum of the forces, just says, hey, go look at your forces and pick the ones that are in the x direction. And so this gives us the two forces in the x direction are F, that's this guy, and the friction force, FF, that's that guy. And we notice this guy is in the plus direction. Our push force is in the plus direction, so I can put a plus there or not. It's assumed to be positive, right? And then and I get a minus sign here because my friction force is pointing backward, right? And that's equal to the mass times the acceleration of the object. Or I can say the acceleration is equal to the push force minus the friction force divided by the mass. Right, that means my acceleration is equal to 10 newtons minus 5 newtons divided by 2 kilograms. Right, and that's 5 newtons divided by 2 kilograms, or 2.5 meters per second squared. So that's how you use the free body diagram to solve a problem like this. As we get to more complicated problems, you'll see why this is where all the action is, the free body diagram. If you can get that free body diagram drawn, which means you have all the forces, you haven't broken up into components, the rest of your stuff is fairly straightforward. And so the key to solving Newton's law problems is being able to draw that free body diagram. So this is another problem, a Newton's law problem where we're going to sort of emphasize the free body diagram. Here a speaker is suspended by cables as shown. So here's a cable, and the tension in that cable we're going to call T1, right? And the direction of that tension, at least as it acts on the speaker, is to the upper left. The cable makes a 45-degree angle with the ceiling, and over here on this cable is T2, right? And it's acting this way, at least as far as the speaker is concerned. And there's one more force acting on the speaker, and that's the force of gravity, and that's equal to mass times gravity, right? And so we've got these three forces acting on the speaker, and we want to determine what the tensions T1 and T2 are. And so we start this problem by just drawing a free body diagram for the speaker, right? And so let me get a different color now, maybe Let's make it look a little different. Whenever we're drawing a picture, we draw a free body diagram, we draw a dot for the object. And so that's our speaker. And then going off in this direction, I have T1. Let me just clean that up a little bit. Maybe I'll do it up here. T1. And then going off this way, I have T2. And going down this way, I have the force of gravity. And when we're drawing our free body diagram, the next thing we do after we've identified all our forces is we define the direction of the acceleration. Sometimes it's not clear. This object's at rest, and so if it were me and I thought, well, I would just put A equals 0, but I may give it a little downward direction, because if it fell or something, that's the direction it would want to go. And so it doesn't matter too much what coordinate system I pick, and so I usually pick just a standard one in those cases, which is X for the horizontal and Y for the vertical. And so now I'm almost to the point where I could just go off and solve Newton's laws. I could come over here and I could say, well, look, the sum of the forces in the X direction equals ma sub X, and we know that that's going to come out to be 0. Let me put a little X there, because the object isn't moving. It's a speaker that's hanging at rest. Sum of the forces in the Y direction equals ma sub Y. That's also equal to 0. And so all I've got to do is get the forces and plug them in here and set the whole thing equal to 0. The catch is that I don't have forces that I can plug in here. This T1 doesn't fit into either of these categories, an X direction force or a Y direction force. And so I have to find some way to arrange it so that it does. And anytime I have a force that's not on one of my coordinate axes, I have to find components of it in that coordinate system. And so in this problem, I'm going to have to pick my my T1X going to the left and my T1Y going vertically. I break this T into components. We've already said that anytime I can represent one vector with two others that add up to it. And so I'm going to represent T1 as T1X plus T1Y. And now I do each of these guys is along a coordinate axis. And I even know the relationship. I can say, you know, the magnitude T1 is equal to T1Y is equal to T1 times sine of 45 degrees, because if this angle up here is 45 degrees, then this angle is 2, and so that means this angle is 45 degrees. Similarly, T1X is equal to T1 cosine 45 degrees. And so that gives me T1 X and Y in terms of T1 and the angle I know. And so on the next page, I'm going to redraw this picture with just the components, and we'll get a free body diagram that we can use to plug directly into the Newton's law equations. So I've redrawn the partial free body diagram I had earlier, and now I'm going to clean it up. Usually once I've written my components for my vectors, I redraw my free body diagram a little more cleanly. And so here I have my object, and now I have an upward direction, and this is T1Y, and I have a horizontal direction, and that is T2. The other horizontal direction is my T1X, and my vertical direction is the force of gravity. And we know that T1Y is equal to T1 times the sine of 45 degrees. And we know that T1X is equal to T1 times the cosine of 45 degrees, because those are the X and Y components of the T1 tension vector. And so my coordinate system here looks like the one I have over there to the left. I have an X and a Y, because my acceleration was, even though it's 0, I gave it a direction of downward, right? And so now I've got a clean free body diagram with all my forces pointing along coordinate axes, and I can come over here and I can say, look, the sum of the forces in the x direction equals ma sub x. Since the object's at rest, that's at 0, right? And so that tells me that t2 minus t1x is equal to 0, or that t2 is equal to t1 times the cosine of 45 degrees. So this doesn't solve my problem, but this gives me one of the tensions in terms of the other, right? Now I can go over and I can grab my sum of the forces in the y direction equals ma sub y, and that's equal to 0. And this says that t1y minus the force of gravity, which is pointing downward, is 0, or that t1y is equal to mg, right? And that says that t1 is equal to mg over the sine of 45 degrees. That gives me t1 is equal to 300 newtons, because the mass was 30 kilograms times 10 meters per second squared divided by 0.7071. That's the sine of 45 degrees. That's 424 newtons. This gives me T1, right? Now I can grab this equation and say T2 is equal to T1 times the cosine of 45 degrees, and that's equal to 424 newtons times 0.7071, because the cosine of 45 is the same as the sine 45, and that gives me T2 is equal to 300 newtons. And so these two, sorry, that should have been a 1 down there, these two are my answers, the two tensions in the problem. And we got to them largely by just using the free body diagram and then plugging in.